Let's take some time to develop the derivatives of e to the x and the natural log of x. For the derivative of the natural log of x, we're going to have to use our definition, which is limit as delta x approaches 0. We'll have x plus delta x in the first function, subtract off natural log of x, and divide by delta x. Now, I know how this is going to go, and it's going to get kind of messy if I continue to use all these delta x's. So I hope you don't mind. I'm going to change the delta x's into h's. And that is literally just to clean things up. So instead of x plus delta x, we'll have x plus h. And in the denominator, instead of delta x, we'll have h. Now, trying to evaluate this limit isn't easy. We're going to have to use some algebraic properties that we know. For instance, instead of dividing by h, I'm going to multiply by 1 over h. And we also have this other property of logarithms that says if we are subtracting two logarithms with the same base, we can rewrite that as a single log being the quotient of x plus h and x. Before I do my next step, I'm going to do this nice little math trick I know where I multiply this fraction by 1, and the specific version of 1 that I want is x over x. So that when I rewrite my limit, I'm going to take that part and multiply it together and split it all up so that I have 1 over x times x over h. And inside the natural log, I'm going to simplify that as 1 plus h over x. There's another property of logarithms that we can use, and that is the power property. The power property says if I'm going to take a logarithm and multiply it by something, that something can come up as a power up here. And that's how I'm going to rewrite this, as the natural log of 1 plus h over x to the x over h power. Now I have that natural log almost in the form that I want. I mean, it still looks pretty messy, and so I do want to clean it up a little bit. What I'm going to do is define this variable n as being h over x. And what that would mean is that 1 over n would be x over h. And we can use that in our limit. So I'm going to change that h over x into an n and the x over h into 1 over n. Now that does mean we have to change our limit as well because we don't have any h's anymore. We have n's. So think about, the limit as h approaches 0 of h over x. That would be 0, right? So instead of h over x, I have n. If I want the limit of n to be 0, then n would have to approach 0. So that's what I'm going to change my limit to. Now, I hope by now you've noticed something in the way that I've transformed this natural log, that the limit I'm looking at specifically that I want to take care of is this limit as n approaches 0 of 1 plus n to the 1 over n. Now, we've dealt with this a little bit, and through inspection, we've already found that that limit is going to be e. So when I evaluate my limit over here, let n approach 0, well, if n's going to approach 0, 1 over x stays 1 over x. And 1 over n, or 1 plus n to the 1 over n, as n approaches 0, is going to approach e. Natural log of e, those are inverses of each other. So they're going to cancel each other out here and here. And the only thing we're left with is 1 over x. So our result is the derivative of the natural log is 1 over x. Seems kind of non-intuitive that that natural log is going to have a derivative that's 1 over x, but it does. Next, let's take a look at e to the x. So let's let y equal e to the x. Then because e and the natural log are inverses, the natural log of y would be x. Now, I hope you don't mind if I rearrange this. So it's x is equal to the natural log of y. But we can find that derivative. We just showed that the derivative of natural log is 1 over. So this would be 1 over y. Now, we have this, I just use this x prime notation. And I want to take a second here. We're used to seeing y prime. You know, that was Newton's notation. And Leibniz would have written it as dy dx. Now, where we're at, we have x prime, as Leibniz would have written it. That would be dx with respect to y, the change in x with respect to y, because our function is now written in terms of y. So I could write this as dx dy is equal to 1 over y. But we want to find the derivative of e to the x, which would be y prime, or dy dx. So I need the reciprocal of this. But I got one fraction equal to another fraction. And this really is part of the brilliance of Leibniz notation, is that we have dx over dy. That is still acting like a fraction. So if I take the reciprocal of that, dy dx, then I take the reciprocal of 1 over y as well, which is y. And we said in the beginning that y is equal to e to the x. So what did we just show? We have our result right now. That if we want to find the derivative of e to the x, it's going to be e to the x. There's only, one of the few functions where its derivative is the same thing as itself. So we have two nice results that we need to just have memorized. The derivative of natural log is 1 over x, and the derivative of e to the x is e to the x. Now, if we want to find these derivatives, we'll just take them term by term, and f prime is going to be the derivative of natural log, which we said was 1 over x, minus the derivative of square root of x. Remember, square root of x is x to the 1/2 power, so we can use power rule. 1/2 x to the negative 1/2. And derivative of e to the x is e to the x. If we want to take the derivative of y, dy dx is going to be term by term. We use power rule on 3x squared. That would be 6x. 4 over x, remember that's x to the negative 1. So 4 times x to the negative 1 would mean, instead of adding, we're going to subtract 4, x to the negative 2. And our last term, even though we're multiplying e to the x by 7, we can use that constant multiple rule and go 7 times the derivative of e to the x, which is e to the x. And if we want to find the line tangent to g at 2, remember we need two things. We need to have a point. The x-coordinate is going to be 2. We need to find the y-coordinate. So we just plug in 2. That'd be e to the 2 plus the natural log of 2, which is a number. That's the exact value of our number. We could go to the calculator if we want and find a decimal approximation for it, or we could keep the exact value. The other thing we need is the slope of our tangent line, which of course is the derivative. So the derivative of g of x is going to be e to the x plus 1 over x, which means derivative at 2 is going to be e to the second plus 1 over 2. That's our exact slope. Here is our exact point. So if we want to write the equation of the line, we'll go y minus the y-coordinate, e squared plus natural log of 2, is equal to slope, e squared plus 1/2, times x minus the x-coordinate, which was just 2. And that's the very exact version for the tangent line.